Welcome to third video on system of particles and rotational motion. So in this video I am going to discuss expression for center of mass of a thin rod. See, we already came to know that how to write the position coordinate of center of mass of two particle system, three particle system, and in general we have written this position coordinate of center of mass of the ith particle in general as R is equal to summation of mi Ri vector divided by m, or 1 by m into summation of mi Ri vector. So this is the position coordinate of the center of mass in case of system of particles. Suppose if you consider regular rigid bodies, like what we have taken in this case, a thin rod is a regular rigid body. This thin rod has composing very large number of particles. We cannot identify the individual particles. So in such cases, the summation is replaced by integration. Therefore, in such cases, we write position coordinate of center of mass in case of regular rigid bodies like sphere, cylinder, metallic rod, etc. as R is equal to, the summation is replaced by integration symbol. So 1 by m into integration of vector R dm or I dm is Ri dm. So this is the general expression that we can take to find the position coordinate of regular rigid bodies where we cannot count the individual particles, as a vector R is equal to 1 by m, where m is the total mass of the rigid body, into integration of Ri vector, which is the position coordinate of ith particle, into dm. So I will use that concept in this expression. So consider a rigid thin rod whose width is very small compared to its length. Let dm be the small mass on either side of this axis of rotation, where this axis of rotation is passing through the center along their length. So dm is the small mass element on either side of this axis of rotation, which are at a distance x. So now let us know what is the expression for center of mass of a thin rod. See from figure, for every element of small mass dm on positive x-axis at a distance x, we have an equal mass element dm at a distance x along negative x-axis. For every mass element dm at a distance x along positive x-axis, we have an equal mass element dm along negative x-axis at a same distance x. So therefore, net contribution of every such pair to the integral is 0. So every contribution of such a small mass on positive x-axis, we have equal mass on the negative x-axis. Therefore, net contribution of every such plane to the integral is 0, that is integration of x dm. Integration of x dm is equal to 0. Since integration of x dm is equal to 0, which means in this case the center of mass of a thin rigid rod coincides with the geometric center, that is coincides at the center of the rod. So therefore what we can conclude in this expression is, in case of a thin rigid rod whose length is much larger than its width, the center of mass of the thin rigid rod coincides with the geometric center because integral of x dm is equal to 0. So now we can see some general factors related with center of mass. That means center of mass of a rigid body depends on shape of the rigid body and also distribution of mass with respect to axis of rotation, because if you shift the axis of rotation from center to a side, then center of mass is going to change. Therefore center of mass depends on shape and distribution of mass of the rigid body. Then in case of regular rigid bodies like a solid sphere, a solid cylinder or a circular disc, etc., we call them as regular rigid bodies. In those regular rigid bodies, center of mass coincides with geometric center, that is center of the sphere and center of the disc, etc. Therefore center of mass coincides with geometric center of the rigid bodies if the rigid bodies are regular rigid bodies. And from this discussion, what we can conclude is, center of mass is the balancing point of the rigid body. That means we can balance the entire rigid body after choosing the center of mass of that rigid body. Therefore, center of mass is the balancing point of the rigid body. For example, if you take this is an object, if the center of mass lies exactly at the center of this rigid body, so I can consider the center point as the center of mass of this rigid body, and I can balance this object from the center.